Okay, well, good to see you guys. There's a big crowd today, so welcome. Exploring the Colpitts Oscillator and other circuits with LTspice. So here's the little agenda that we're going to go through. A little introduction, and I'm going to show LTspice working with just an RC circuit just to get you going on what it will do. And then we're going to talk about what a Colpitts Oscillator is. We'll talk about how it works and some of the basic parameters about the Colpitts Oscillator. And then we'll actually put the Colpitts Oscillator into LTspice. Give it a whirl there. That's where you can start to see the power of what LTspice does. We have an oscilloscope view of what comes out of this Colpitts, the waveform. We'll have a spectrum analyzer view that's all part of LTspice to see what the frequency looks like coming out of an oscillator. We'll do a few filters, low-pass filters, and then we're going to play with a couple of direct conversion receivers. We'll talk about that, and then a couple transmitters. So, introduction. My name is Craig Johnson, and most of you know me, but A0ZZ. I was originally a ham back in 9th grade, and that was likely which got me going into wanting to be an electrical engineer. My family all went on to be doctors and things, and I said, no, I want electronics. Anyway, so we had a big gap in there when I was in college, and I was doing software and so on. And then after, when I went to work for Unisys, I was doing software development for many years. So most of my career has been in software, for good or bad. And the only engineering I did that time was hobby stuff. So back in about 1995 again, I got relicensed along with my kids. So they dragged me back into it, which was interesting. And so we got relicensed, and then I saw the overlap between software and hardware, and that was what really turned me on. We didn't have PCs back when I was first doing it, and all the digital stuff now. And then LTspice and spice simulation are one of the things that really turned me on, because I could try out a circuit, I could use software, but I could see how a circuit worked. I've learned so much with simulators through the years, and it's just been one of those things that's really helped me a lot in my engineering career. Fortunately, after 35 years of software, I switched over in the last 10 years before I retired. I was doing hardware development, medical devices and things. Like the pump that Dave wears right now is one of the products that our company that I worked on. So that was really a thrill. But anyway, LTspice, I still worked even at Smith Medical. I used LTspice to simulate some of the circuits that I didn't quite understand. How does this work? And I could put it into Spice, and I could look at things and vary parameters and see how it worked. So, LTspice is linear technology, is the LT part of it. There's all kinds of versions of Spice that were originally done by the government. And but linear technology made a version of it. They all had to put their own wrappers on it, or their own user interface. And that's what LTspice does. Linear technology put it on basically to sell their parts. They have a huge selection of op-amps and all that kind of stuff, and every one of them have a great model right there in the library. So easy to pick up, pull into your model, and I guess I better use that when I make my product. So that was very well known that was their reason for it. But you could bring in all these other models too from other vendors, so you don't have to be stuck with just linear tech parts. Linear tech was bought out not in the last year or so by Analog Devices. Analog Devices is the one that's made our DDS chips and things like that for years, high-end op-amps, all that. So now, actually, you get it available. You buy it from, or you get it as a free download. You get it from Analog Devices website. I had a handout to bring to you all, and I left it at home. So I'll have to put it on the website or email it where to load LTspice. And also, I have a handout with it has a couple of, we'll get into that, a couple of tutorials done by friends of ours that are really very good. So, anyway, so that's, LTspice has been a very powerful tool if you really want to see how a circuit works. There are some limitations now, and, my friend Rick Campbell, KT7B out in Portland State, is a professor. He has his students make things in LTspice, then make the real one, and then say, well, which one is correct? Well, obviously the one that he built is correct. Now, he said, make the model match that. Okay, so you have to add in a little stray capacitance, you have to add in a few other parts. See how close you can make the model go to the real one. And that's not as easy as you think sometimes, because LTspice is going to give you an idea, or get you in the ballpark, but it's not the real thing, okay? It's going to get you close. It'll tell you some of the and I built a lot of circuits, and I built them first at LTspice, and then I build them, and boom, they work the first time. So it's close enough for, you know, and then you do tweaking if you want to increase the performance or some particular parameter that you want to optimize. So anyway, LTspice, a circuit. I'll just show you the very basics here of how this works. Now, so this will be, I'm going to start out with a blank sheet here. And by the way, you get the blank sheet once you open it up by going to up in the left and upper left corner to File and New Schematic. Okay, so that's what I have here, the new schematic. And I'm going to just pull in a couple parts here. You can see how this is done just off this top toolbar. The little one over there, I think you can see the mouse pointer to it. It looks like a little AND gate, but you click on that. That's the location of their parts library. And you open it up and you slide the slider across over here to a voltage. Click on OK. I'll put that right there. And I'm going to put just two other parts right up in the top bar here. There's a resistor. It's a real common parts. There's the resistor here. You bring it down. By the way, to rotate a part, it's a little different. Each tool has its own way of doing this, but it's Control R in LTspice. Control R will rotate it around, you know, any way you want it. Okay, so I'll leave that there, and then I'm going to get a capacitor up here. Now, and I'll connect these together. You go to the little pencil up here, and you see that in the upper corner? And that's the wire tool. And so I'll start here, and I'll go up here, and you can draw right through the resistor. You don't have to stop at the ends, and right through the capacitor. Bring it down to the bottom, and I'm going to put a ground down there. That's also in the upper bar. By the way, how many of you used LTspice in the past? Okay, several of you, or other spice tools too. I know there's lots of them, but this is just one free one, and it's very, very well supported. So it's just one way to do it. Okay, now so there's the basic circuit that we're just going to look at. And now, how do you put some values in it? Well, we're going to put the voltage. I'll just right-click on that, and I'll say I'm going to put 5 volts in there. And for the resistance, I'm going to say 100 ohms. And for the capacitance, I'm going to say 10 microfarads. Okay? Now, we start telling how long we want to simulate and all that kind of thing, what we want to look at by going up to the simulate. Do you all see where the mouse is, by the way? If I don't, otherwise I can use a pointer, but I think you can see it better by just using the, okay, simulate. And then edit simulation command. And here's where we're going to tell it. We're doing a transient analysis in this one rather than an AC analysis. I'll show you the difference there. The stop time, I'm going to stop it at like, say, 2 milliseconds. By the way, in LTspice land, if you want a 2 meg resistor, you don't say 2M, okay? Because that'll go to milli every time, no matter if it's capital or small. You want to say meg, 2 meg, and then you've got meg ohms, okay? Otherwise, that'll throw a lot of people. So 2M is 2 milliseconds. I want to start starting right at 0, and I want to say a maximum time step of 0.1 microsecond. I just, you can vary that, but that's just a good starting spot for. And I'll put this down at the bottom. You just paste that on the bottom, and Spice will pick it up. Sees that little dot in the front of it and says, "Oh, that's a Spice directive. I'll pick it up and I'll use that." So this is going to start at 0 and so on. So now, to run it, you see the little running man up in the corner. You poke the running man. That's what the guy that wrote LTspice, it was a privilege to go to a seminar. He was down in Bloomington a few years ago. Our company sent me, and he was drawing this, and that's what he always said. I poke the running man, and then he starts to run it. So there's the basic layout, and I'm going to just move down into this side, and I'm going to just click on the waveform where I want to look at it. So this should be a resistor charging a capacitor, and we should, oh, I forgot something. I'll show you what it is. It looks like it's always there. Back in the simulate tool, there's a little box down here right in the middle. It says start external DC voltage is at 0. That's the one you want to click for this. Otherwise, it's going to go back to the steady state and says, yeah, it gets up to 5 eventually. And so now I'll go back and I'll just click the running man again, and now you'll see now you see the waveform charging up is, I'm going to do it one more time and I'm going to go on a little farther. I should come in, I'm going to go up to, see, 5 milliseconds instead. This is so quick it doesn't matter. And we'll run. Okay, now the thing to look here, obviously it's showing how a capacitor, the voltage on the junction between the resistor and capacitor is charging up to eventually get to 5 volts when the capacitor is fully charged. Now, the thing you think about a capacitor is what? Time constant, right? RC. So if you multiply R times C, 100 times 10 to the minus 5th, so 10 to the minus 3rd, so 1 millisecond should be the time constant. So at one time constant, a resistor is going to charge to 62%, approximately 62 point whatever, of the full value. So we look here, 1 millisecond, just see what happened there, and there we are at 3.2 or whatever. You know what? If I made this if I change this voltage to 10 volts, then we'll read it off directly. Why not? Huh? So 1 millisecond, we got 6.3 volts. Okay. Now one more time constant, so at 2 milliseconds, it's 62% of that difference again. So it's up to whatever. So anyway, you can see the basics. There's the basics of LTspice does it, and you can see the waveform so easily with a probe. You can look at any point you want. You can see the current running through this 100 ohm resistor. You just, instead of pulling down, having a probe on a wire, you just slide it over and it turns into a probe tool. And you click on that, and that'll show you the current. The current is over on the right side. I'm going to have to decrease the size here a little bit, I guess. That's interesting. Because you're not seeing the scale over there. Showing up over no, it's still not. What's that? Yeah, it's.
If you look behind the screen, you see it.
Oh, it's over there. Oh, yeah.
Does the projector have a zoom that we can bring it?
No, I'll just move it over a little bit. There you can see it. So you can see the current going through that resistor at all the different, places until it finally gets to fully charged. So anyway, that's just real basic, but it shows you how to enter a simple circuit in the LTspice. And that's what I wanted to show in this part. Okay, so now we'll go back to the PowerPoint and RC circuit. So the next thing we're going to do is a Colpitts Oscillator. Now, here's a real nice Colpitts Oscillator, but it's a little more complex than necessary. And then you see here's the Colpitts part of it is right with the heart of it is this transistor, the Q1 here, and then this part of it right here is the Colpitts. This is a buffer that's added onto it too. This is really a full transmitter. If it's crystal control, if you want to make a full transmitter and hook a low-pass filter out here, you'd probably get a watt or two out of this one, just the way it is. You have to key the 12 volts or some other way of keying it to turn it on and off for CW. But basically the Colpitts is this part of it, and it's driving some other stabilizing circuit and power amplifying circuit. So Colpitts Oscillator, the key thing to know, of course, is you always recognize it with the split capacitors here, right? Hooked from the base to, and then hooked to the emitter. And then the crystal is hooked out in here somewhere. Now this 68P obviously is not being used right now. It's shorted up, but this is if you want to pull a crystal a little bit, you can hook out a capacitor here instead of this short. Right now it's shorted out, but so that's where the crystal hooks on, and there's your basic Colpitts Oscillator in a pretty fancy circuit. It's really a nice one to build. But here, this is an LTspice drawing of it, because I want to go through some parts of it. And once again, we see the same 22 and 2222 is a real good transistor port. And the split here, those two values are pretty good for 7 megahertz. And those two for bias, I'll show you that works. And this is how you model a crystal in LTspice. You have an inductor and a capacitor. And basically at 7 megahertz is about 40 ohms of series resistance in it, and about 4 picofarad for the capacitance of the case. So basically, you want to do what want to get a resonance between these L1 and C1 to make it resonate at the frequency that you want. And we'll show you how that works. So, now, what's the bias of how you want to set this thing up? The first thing I did is I disconnected the wire to the crystal, okay, because I wanted to see what the DC view of it looks like. And the bias here is set up like 12 volts coming down this 10 mil is virtually, I don't care. And so really you have 82K and 120K with 12 volts on the side, top. So you see the bias is really going to be 12 volts times then this resistor divider. So you take R2 over the sum of these two, R1 plus R2, so you get 12 times 120K over 202K. That's about 7.1 volts. Now it's a little bit different because this is taking off a little bit with the base current going through there, but it's very close to 7.1. Now the other part, how much current is going to be going through R3 down here? Well, if you have 7.1 volts here and 0 here, that means you have 7.1 here. And you take off about 7/10 of a volt for this emitter. Okay, so down here you have 6.4 volts. And so you take 6.4 divided by 4,700, 4.7K, and you get about 1.3 milliamps. So very quickly you can see, this looks like pretty good values. 4.7K is reasonable. 10 ohms is reasonable. We're going to get about the right bias on the transistor. That's all set up pretty well, and with a crystal on there, hopefully it'll work. Now, how do you get the how do you model a crystal? How do you get the right values for L1 and C1? Well, you can remember a couple of formulas. Remember the frequency of a LC circuit? Frequency is 1 over 2 pi times the square root of LC. Remember? Now, how do you get the reverse the F and the C? You do it by squaring both sides. Get rid of that square root. So now C is 2 pi F, all that squared, times L. Okay? And then this is another way of writing it in one line, and that's the way it's done for LTspice. You put it in the one line like that with a number of brackets, and you can actually specify it that way. So that's what we're going to look like for the crystal. Now, we're going to put parameters in like that. I'll show you how we do this, but this is how LTspice is going to pick up those parameters. You see, instead of a fixed value for the inductance, I'm going to put an LS, a series inductance, and I put it in brackets. And brackets tells it that LTspice is looking for a formula. What is LTspice? It's going to look over here. LS is F0 over 1 e to the 9th. What's F0? F0 is 7 e to the 6, or 7 megahertz. 1 e to the 9th is an approximation for a 7 megahertz crystal. We just know that it's about 1 e to the 9th. This isn't going to be perfect model, but it's going to be close. And then what is CS? Now CS, we will put into the formula up here, and you write it out. So 2 pi F0 squared times LS. That's pretty close to, with those values, those two will resonate, and it should make a resonant crystal at 7 megahertz. So we'll show you how to do that. Now we have a demo of how to do that. This is the same we had. We just looked at all those parts. It has a transient, another spice directive at the bottom that tells it to, I'm going to run for about 6 milliseconds and so on. But let's start off with a blank, and let's see how we're going to put some of those components in there again. We're going to start out by dragging I'm going to find a transistor down here, and that's under NPN, right there. And I'll say OK. I'll plug that right in the middle here. I'm going to find a voltage source, and I'm going to go over here and do the voltage source like we did before. Okay, I'll put that up here. And I'm going to put a resistor up here, like we said. And a resistor down below. Make this a little bit smaller so we can get everything on it here. Oh, that's two other important things. You see up here where the cursor is? You see the little two hands? Okay, one of them is to move and one of them is to drag. So if I want to drag a resistor, drag a resistor, you click on that hand, and you click on the body of the resistor, and you can drag it around. And you can't do that unless you have the drag tool, highlighted. If you want to cut it or move it, this will keep the wires connected, by the way. I haven't done that yet, but it'll keep the wires connected. If you want to move it to another spot in the schematic, you just take the component out, then you use that other one there right next to it. I'm going to just real quickly. I'm not going to draw the whole schematic here. I'm going to jump ahead, but after we get a couple of the basic components here, we'll go to the fully built one. But I just want to show you how it's done. Now, how do you specify a resistance value? We did that before. We click on that, and we say I want a 4.7K, and the NPN. Now, how are we going to get what kind of transistor is that? Well, if you right-click on that, you say pick a new transistor, and then you can go up to the part number to put in order here. And you look down to the list, and it happens to have a nice model of a 2N2222. So you say, okay, you could have used a variety of them, but that's just a nice basic one. And I'm just going to do a couple more parts here, and then I'll stop and go to a fully built one. Put a resistor for the bias, resistor for the bias, capacitor, and so on. So I think you can see, how you drag in the basic pieces from the library. And the library's got lots of parts. Depending on the one you want, you can add it. And a lot of the parts the models are available on the internet if you want to go searching for them. Otherwise, they have a pretty good selection right there in their standard library, which they keep updating. Okay, so now rather than complete this thing, and this, I'm going to just jump ahead. This takes too long. Okay, and I'm going to open up a crystal oscillator, and there it is, just like we had before, except now it's actually in LTspice. And I'm going to click the running man. We'll start a simulation here. And in just a minute, we'll be able to look. Oh, by the way, I connected one other thing to it. You can see, I connected this capacitor, this feed-through capacitor and a 10 ohm. I put a load on there so we can be able to look at this spot here. Okay, just to terminate it a little bit differently. I'll click on the probe there, and that looks like a blob. What is that? Well, this shows you that it takes about a little over 0.2 milliseconds to get the crystal going, right? The oscillator is just dead until finally gets there, and then it starts to pick up speed, and then it goes more and more. Now, what's going on here? By the way, this is I'm already on to the next slide, which says, what's the oscilloscope view of this? This is what you'd look like. Well, obviously, that doesn't help you too much to see the waveform, but you can quickly change the scale on it, okay? And you could just go up here and you could select a part of it. You say, I just want to take this much of it, a sliver of it. Oh, that's still too much. Okay, and then you could say, I want to do it again, I want to just take this much of that. Boom. Now you can finally see the waveform. Okay, now it's a little peaky, right? It's not particularly round, but that's kind of a typical of a crystal oscillator before it's buffered. And it's going from minus 2.4 up to plus 3.2. That's a nice solid signal coming out of the oscillator. Now, you want to say, what frequency is it running at? Now, this is the next slide, but I'm doing well in here. There's a couple ways of doing this. One thing, you could start over to the left. You could say, what's the time frame here? Okay, 891 microseconds. What is it over here? 896. And you can count the number of pulses. And divide it by this time. How much time elapsed, okay? Then you'll have the frequency. But there's an easier way. Well, in fact, you can actually you can tell it to go from 1 millisecond to 1.01 milliseconds, okay? And then divide it, and you have a nice even, and you can see how many, you can count them very direct. You don't have to worry about the complicated math of subtracting these two and counting that many pulses. But there's an easier way. In LTspice, has got a very cool thing. You go into the waveform, you right-click, and then you go down to the very bottom here, and it says View, and then FFT. You know what an FFT is? Fast Fourier transform. That's like a spectrum analyzer view. Now you're changing from the time domain to a frequency domain. In other words, the bottom base is going to be frequency instead of milliseconds. And this does a fast Fourier transform as a kind of a shortcut to make it modelable. Otherwise, it's too complex. But it's a quick way of making a quick spectrum analyzer view. And there's only one view that I'm looking at right now, and there it is. Now, you can see that here's 10 megahertz, so 987. Ooh, you know, the fundamental is right there at 7 megahertz. You can also see a nice spike at 14, 21, 28, and so on. These are harmonics that just happen to show up here because this is not filtered at all. But there's the nice, in other words, this shows that our crystal worked, and the formula worked, and this actually made a nice output right at 7 megahertz. So this spectrum analyzer view of it is phenomenal. It's really handy to see what the frequency is coming out, and we'll use that to get a little bit of audio. So anyway, so now we'll go back here and go back to the PowerPoint again. And so then we looked at the oscilloscope view, see you later, and we looked at the spectrum analyzer view. So now we're going to look a little bit about filters, another kind of thing that's really handy to look at with LTspice. And take a second here to open it up here. And the first one I'm going to look at is just a low-pass filter. And that's the only components you have to really enter in, just like that. This is one that I kind of played around with, modified somebody else. And just a basic low-pass with 2 inductors and 3 capacitors. You see that all the time. And now what does it look like? Now this one we're going to use a little different view of it. Under Simulate, Edit Simulation command, instead of using a normal transient, we're going to use this AC analysis because we want to have a span of frequencies and instead of a span of time. Okay, so then you put in about 100, these are some pretty standard values that seem to work, and I wanted to start at like 6 meg and I wanted to go to 14 because this is a 7 megahertz low pass filter. I don't want to see all the stuff out to the left, and I want it to cut off at 14 because I want to see what that second harmonic looks like. Now, if I start at 6, I'll be able to see the knee, and I'll also see right there at 14, it'll give a value, and you can read it up directly as to how much suppression you're getting for that second harmonic, which is the key factor. That's what the FCC is requiring it. So, hooked already, man, and I'm going to look at it right at the output, right at the antenna. Now, you can see that this one's going to, the knee is at about 7 megahertz. Give or take, pretty close, and it goes down at 14, stop the screen, it's about 43 dB down, which is the magic number. That's what FCC requires, is the second harmonic be 43 dB down. Now a lot of them aren't that, but by the time you go through a tuner and everything, by the time you actually radiate your signal, a lot of them, even though the model says they're not 43, they would be, but this one right now, just right on the blocks, you know, this says this is sufficient to give you 43 dB of suppression on that second harmonic. And the rest of the harmonics are down further than that, so you don't even have to worry about them. Although you could if you wanted to spread it out and look at them. Okay, so now I'm going to look at just a couple other of these. I'm going to look at, here's, you know the famous MC40A by Elecraft? This was Wayne Burdick's first rig. I think before he started Elecraft. This is the one he designed for the club out there. I know Jay, I think, is building one, and Chuck is building one. This is a real classic little QRP rig. So now we want to model that. Kind of fun. Just to see what it was. Now, by the way, this was developed back in the day before the FCC was quite as stringent. And the requirement wasn't 43 at the time. It was something like 32 or 35 dB, I think. And so that's why this one, you can't see it. But once again, you can see it's pretty good at 7 megahertz. That's what it's designed for. And it tails off, but when it gets down to 14 megahertz, what is it? 22 dB. You say, you know, that's not really red hot. You know, that's not quite as good as, you know, we're doing nowadays. But at the time, it was fine, and it's QRP and go through a tuner, and you're getting there. But I'm just showing that little different typologies. You can type in, you can change values, you can see what it would look like. How much suppression will I get if I use those values for it? I'm going to just show you, you know, the K1 is the Elecraft early one. Mert's got one, I've got one. It's a little more advanced. It's a digital display on it and everything. They've improved this one a bit. Once again, the knee is about, well, it's all the way up to 7.6 or something, which is fine. And at 14 megahertz, it's about 30 dB. So it's not, quite there, but it's not bad. 29 dB. Now I'll show you one that I just made for that little rig. I was showing you the little 5-watt rig. By the way, I got that putting out 5 watts now, 5.2 watts by tweaking it slightly. And here's a low-pass filter I designed for that little guy. Okay, now this has got a special little tweak to it. And then it's got this little extra capacitor in here. The capacitor, I'll show you how that works. It's going to put a notch in there, right at 14 megahertz, which really brings it down. This has got a matching section also in here, which because I have 14 ohms at the power amplifier. Instead of, I'm not going 50 to 50, I'm going 14 to 50. So I have this inductor and capacitor to convert this 14 ohms up to 50 ohms, okay? And so that's what these two do at 7 megahertz. This 0.1 is kind of a don't care. It doesn't even show up at RF. It just goes right on through it. But it's necessary here because it blocks the DC going into your low-pass filter. So you still stick that 0.1U in the circuit. And then from then on it's 50 ohms, kind of like we did before. And I'll show you what this looks like. Now, you see at 7 megahertz, it's just right there, it's full until 7 megahertz plus. And by the time you get to 14, if you go to, we don't even count the bottom, say it's a little bit off 14, you're still down to 80 dB. I mean, that's really suppressing that second harmonic. It's really a nice filter. I want to just show you quickly what it looks like if you just said, what would it look like without that capacitor in there? So, you go up to the little scissors up there, by the way. That's how you get rid of a component. Click on the scissors and you come down here and you say, snip. Okay, now what's this thing going to look like? So you poke the running man. What does it look like? Well, 7 megahertz is still pretty good, but 14, 36 dB now instead of 80. So you can see the value of that little capacitor in there, making that notch in there, really brought it down. It was very powerful. Sometimes there's, multiple sections that they put it on the second or third one, but there's, various designs. But this was a very powerful little topology to make a nice low-pass filter, and that's the one I put in the little mini rig that I built. So, now we go on. I'll get into this stuff here. Oh, hairier now. Now we're going to go look at some direct conversion receivers. The first thing I want to do is a little review, okay? Remember when we built the ZZRX40, the little receiver that I built?
Well, not quite.
What's that? You don't quite remember?
Mine didn't work.
Oh, well, some of them worked. 99% of them worked. Anyway, Mert and I did a little, as we were soldering the thing together, remember Mert and I did a couple breakout sessions where we talked about the theory of how this would work. Some of these are slides from that. I want to show you a little bit what a direct conversion means, how a mixer works, because I'm going to try it in LTspice in just a second here. So basically, these are the basic components of any, back to the full screen here. In any receiver, you're going to have an antenna coming in, you're going to have a mixer, you have a local oscillator, an audio amp, and a speaker. Now, the ZZRX is really, this is about bare bones. I mean, there's a little bit of matching and a couple things, but it wasn't much more than this. You can make it a lot better and, fancier by adding more components. So now, how does a mixer work? Well, these are artificial components, but just to show you the theory of how it works. If you had an incoming signal at 10 hertz, local oscillator at 8 hertz, what are you going to get out of a mixer? You're going to get the sum and difference, which is 18 hertz and 2 hertz, right? And then look at the audio amplifier, and what are you going to get? You're going to get it louder. Okay, it's just going to get more, even though this is really low, it probably wouldn't even show up. Now, let's do a little bit different. 1 megahertz and 1 megahertz. What are you going to get coming out? You're going to get 2 megahertz and 0 megahertz. Well, this has got a low-pass filter in it, so you're not even going to get the 2 megahertz. It's going to be down on audio, but you're really going to get 0 hertz out, and you're just going to get noise. You don't have any difference yet. So you're really not going to get anything good out of this yet. But one more step now. if we go and we tune this local oscillator just a little bit, this is still 1 megahertz, we're gonna add 600 to this local oscillator. Now what are we gonna get out of the mixer? 2 megahertz plus 600 and 600. Well, the low-pass filter will get rid of the big ones, so all we're going to get is 600 hertz out of there, which is a nice audio tone. So that says by tuning the local oscillator into a mixer, you're going to get a nice tone coming out of it. Now, one more part of it. Simple the crystal oscillator. Remember, we did this too. There's the Colpitts Oscillator that we're talking about today. Basically the same kind of bias, couple, crystal on there, couple split capacitors. Now, one more step. There's another way of biasing it. Instead of putting those two resistors out here, this is called self-biasing. It's kind of a poor man's way, and it works if you have the right current going through it. You have to kind of calculate, figure out what this resistance value is going to be. It's a little more complicated, but it gets rid of one component. Well, it just so happens, this is the part of the Colpitts Oscillator that's built into an NE602. They actually have this transistor, self-biasing, a resistor down here, and they just have open terminals here that you can hook up the capacitor and crystal, and you have your mixer. This is the basics of a mixer all built into an NE602. In addition, of the oscillator, in addition to the mixer parts. And that's what we used in the ZZRX. We used this Colpitts oscillator, and we just added these three components, and we had the Colpitts oscillator for it. So here's a couple of values that we put on there, typical. Now, I'm going to show you what the ZZRX looks like in LTspice, because I did a model of it, surprisingly enough. Okay, now, you can see this, there's actually a model available online for an NE602. And this one looks like they don't put all the innards in there, but they make a model and they just show you the pins coming out of it. So all we had to do to make an oscillator was to hook up some capacitors, hook up a crystal. So I put the model here just like we just had done. And then I have two more components down here on the bottom. This inductor and capacitor. You wouldn't actually put them both together in series, you do one or the other. But once again, it's a matter of pulling that crystal a little bit. We wanted to tune it a little bit, so we could do it with an inductor or a capacitor down here, not probably both of them. But this is just for illustration. And then down here, the RF signals are going to come in here. We have a signal generator here that I'm just specifying it at 7 even. I'll show you. I'll open it up. When you specify the voltage source, you have your choice. At the top, it's just a plain voltage, or else you can make a pulse or a sine wave or an exponential or whatever. So in this case, I'm saying I want to make a sine wave coming into it, and I want to have a DC offset of 0, 1 microvolt as an amplitude, which is I think it's about an S0 signal. It's a pretty weak one, but it's certainly in the range of the kind of thing that you'd like to hear with a receiver like this. And the frequency is 7 megahertz, 7 even to 6. So that's what I'm just specifying a voltage down there. That's why you see it's so nice to simulate. We're just putting a voltage and making that into a sine wave at the frequency you want, and all these specifications just the way you want them. Then I just do a little bit of matching circuitry to make it match into the 1500 ohms that are specified for the input to an NE602. A little bit of low-pass filter. You see this 0.1 across here? That's going to take the high frequencies and shut them right out, and just let the low frequencies go on through the audio, which is what we want. A little bit of biasing resistors, and then a common LM386 that we used in the rig. Now, unfortunately, this LM386 model is not very good. It doesn't work right in this particular model, and it comes out that it's not coming out with audio. So I modify it slightly to model, and that's what you have to think about. What went wrong? When you model this, why didn't it model the way I thought it to? I made a slightly different one. Yeah. So instead of an LM386 out there, I just took a common op-amp off the shelf, and I just biased it the way it commonly is. Ran in a voltage to it. And I made it with this one with a gain of 100. It took 1 meg over 10K, and that's 100. So it's going to multiply it with a gain of 100. And now this one will run. Let's wait just a second. I want to do the FFT of the audio waveform to see what frequency it's at, just for the fun of it here. And you have to wait just a little bit here. See a little notch in there, by the way. I don't know what that notch was from. There's some component in there that's giving it a little bit of in every waveform. This is really exact because of the model that's being used. You wouldn't see that in real life, but it's there in the model. It's, you know, you could go back and analyze what part of the model is making that little notch there. But every waveform, every time it comes down, it's going to have that little, notch there. Wait just a little bit more here, and then we'll take a FFT view of it.
What's the time scale here?
In 3 milliseconds total here. Okay, 0 to 3 milliseconds. So now I'm going to just click on this waveform. I'm going to go down to View, FFT. This is the one waveform there. And you might have several of them on your picture, and you can tell which one you want the FFT of. And you can see down here, this is 1 kilohertz, 10, 9, 8, 7, 6,500, 6,000. So that shows you that the crystal worked at that frequency, and you know the local oscillator worked, and the difference was what we came up with, and it's very close to 600. And you can see it all in the FFT display. Okay, moving on. Now, another receiver. Oh yeah. Just a minute here. This looks a little more complex, right? But this is the receiver and the little mini DC rig that I'm showing you. This has lots of notes in it, and you do it with just going up to the edit, and you can put notes in there, and I like to do that so when you go back to the model, you can see what you've had before, what kind of voltages you found, without having to run it all and start from scratch again. Typically, coming in the antenna, I just put some typical values for signals that you see coming into an antenna. So right now, I just hit the 140 nanoseconds peak, which is, and that's, let's see it. Anyway, that's just S0. Okay, this is S0 is 27, and this is S9 right there, and so on. So just so I could calibrate it, if I wanted to listen to an S0 signal, it'd be about 140 nanovolts. And what will the output look like if I have that kind of a signal coming in? Now here for the local oscillator, I'm going to set that to 7 megahertz plus 600 hertz and 1.5 volts peak. So 3 volts peak to peak. You always want the local oscillator to be pretty husky compared to the antenna signal. And this is a very simple, it's not the same mixture that we had before, but I'm doing a diode ring mixer, which is very common. I love diode ring mixers. They're very clean. They're still widely accepted as some of the best mixers around. And this one is done with a trifilar winding here. Okay, you've got 3 different windings on the same little core. Okay, you wind the wires together, and then you wind those through the core. So this is 8 turns trifilar on a FT3743. That were my own notes again. And then you get about 20 microhenries on each of those three circuits. There are those 3 inductors in it. Now, how do you tell that there's a transformer instead of 3 independent inductors? Well, that's a little trick. You see that K1 thing here? K1, L3, L4, L5, 0.999. Well, that's a spice directive again. You go up in the corner, upper left-hand corner, you say edit, and then you say, instead of text, you say spice directive. And that allows you to put in values like that. I'm going to click on it. Click on the one I have here. So the K1 is just saying for the first set of, the first coupling, okay? The first coupling, I want to call it K1. Over here, I'll call it K2. And in K1, I'm just going to couple together L3, 4, and 5. 3, 4, and 5, whatever you call them. And at 0.999, that's a really tight coupling. You can change the coupling factor to something less if you think 1 would be perfect coupling. It's a little bit less. I mean, it's probably not 0.999, but something close to that. So that's just a nice way of modeling, saying put a 0.999, see what it says. So there's the first, actually, so this is kind of stepping up the impedance and stepping down the impedance, or the other way around. Anyway, to match And the antenna comes in one of them, the local oscillator goes into another one, and out comes audio, okay? It mixes it very nicely. But down here you have to do some playing around, you have to terminate it, you have a diplexer they call it, to get rid of some of the unwanted signals again. And then it comes on up to a little amplifier here. I'm going to make this a little bit smaller so you can see. There's a simple audio filter. Okay, that's just going to peak it right at around 600. I've got notes down the corner about that too. But a nice little active audio filter. It says peaks at 700 when R3 is set and so on. If I wanted to change it to another peak value, I could change that little R3. And then it just has two little audio amplifiers out here. I happen to use NE5532, a very commonly used low noise amplifier, and set up with a gain of, well, 100 over 2.7K, which is about 37, a gain of 37, which is 31 dB. The thing I want to show you here is I did this whole model of that receiver that I built. There's one more amplifier out here before the speaker. I did it and kind of predicted, because I needed about 100 dB of gain between the antenna and the audio, okay? And I wanted to see what this would set up with these values, what kind of amplification I needed. And so I could look at each one of them, I look at the waveform, I could see how big it is compared to how big the antenna was at the antenna. And I could check out the gain right here. The gain, since the diplexer, was 51 dB. And then I go on to the next one. Here's the volume control. I should have two split resistors. I set them at a fixed at about the maximum right now. And then I get at this first audio amplifier. By the way, the audio filter got a gain of 1.3 already. It's not meant to be amplified. This one gets a gain of 35, which is 31 dB. This one gets a gain of 32, which is 30 dB. And this is just a little mute circuit in here. It's commonly used. You ground this and it'll shut off the flow across J1. So, and then of course there's just a little audio, little ear protection out here with some Schottky diodes so the signal would be clamped if it gets too big. But anyway, so I did all these calculations. You could add up all these gains, or you add up the gains, or you could add the partials. And it says I get 104 dB of gain, right? Well, I went home and measured mine. I inject the signal in here, and I measured on the output 105 dB. I mean, it was very reassuring to see that the math works, and the values that I had selected here were going to give me pretty close to what I have. Now, to actually inject the signal, I have a little simple audio oscillator that I have with an attenuator on it. So I stick the audio amplifier right up here, for example, as the volume control. Okay? And I measure how much signal, I look at my oscilloscope, how much signal am I putting in. Then I put the scope hanging right here on the speaker lead, okay? And obviously it's much bigger. And then I put the attenuator on, pump, 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 10 dB at a time, until I see the signal that I'm looking at now is exactly the same as what I had put in before. Then whatever my attenuator says, that's how much amplification I'm getting. And there it was. I mean, I could look at the various sections. I could put the scope here, or here, or here, and I could look at all the different sections and add them up and see that it came out very, very close to what this model says. So that was really fun. It's fun for me to actually do the math and say, look at that, it came out. I'll just do one more real quick one here. I won't spend a lot of time with it, but it's just another. No, let's go on. I'm going to do a transmitter just real briefly again. Once again, this is my little mini rig. This is all it is to the transmitter. Really simple. I don't have the little gates. There's some gates driving it. Digital gates with some and gates or gates that I'm driving it with, but I substituted this as an local oscillator sine wave here instead. But basically, it's got three MOSFETs on there for the final amplifier, three DS170s in parallel, and then the matching circuit out here that we talked about, exactly what it was. This is going into the low pass. This is this is when you split off the TR switch going to the receiver And so when it's in transmit mode, I'm just showing you, these are disconnected. It's essentially grounded because you're getting a big signal coming through here. This is only 7/10 of a volt high. So it doesn't hurt anything. It doesn't hurt the receiver. That's your TR mechanism. And then you can see the signal going all the way through. And you can still measure the output here with this capacitive actually added to this one because these are in parallel. So, and this is just a little simple keying mechanism. I'm going to put a pulse here at a frequency that'll simulate setting up and down that key. And that's going to just key one transistor, a MOSFET, which is going to key the rest of this. Now, typically in the keying circuit of these kind of things, we use a PNP or a P-channel MOSFET instead of an NPN or N-channel MOSFET because the current flow is better, a little better because of that kind of mechanism. Now, you can see that the particular one I have here, the SI7137, is because I had a model for it. I don't have the model for the one I really want to use. And I say the spec on this one says when it's turned on by the way, when this is a low instead of a high like it is on the other one. But when this is a low, this gives about 2 ohms of resistance across here, which is pretty high for this kind of a circuit. So, and the one I'm looking at, my actually one is an NTD 2955, and it's only 155 milliohms across it. So it's a really nice part for not too much power, and I can hook that in instead, and then run this, and see what it, now I upped this voltage a little bit here because of this resistance, just to see that the output is about comparable. And what else was I going to say here? Anyway, this is going to go on and off. It's going to key this on and off here, high and low, and that'll turn on the power to the S170s. This is going to keep oscillating the whole time, and just by having the power on the finals, that'll tell it to whether it's a transmit or not. Oh, you can see these couple of 1/10 of an ohm resistors up here, one there and one here. Well, those are what I put a little mechanism in there to measure the current. I want to see the total current going through that little 1/10 of an ohm resistor. It really doesn't show up in anything, but I can just click on the little. Okay, I'm not going to go ahead and run these things. It's going to take too long. Oh, yeah, it takes. I didn't start this one out right at the 0. I waited a while because there's a bunch of startup stuff going on. And I just wanted a nice clean waveform. But anyway, you can click on that ammeter on the 1/10 of an ohm. You can see how much current is going to go through there for the whole thing. How much current you can see it oscillating. And I can also put it down here in R3. I can see how much current is going through there. So rather than continue on this, I'm going to stop it. And I just want to show you one other little transmitter very briefly. It's a little more complex again, but here's a local oscillator, and it's just a little buffer, and a transformer coupling, and the key mechanism up here is a little bit more complex because it's 2 different stages, and it's trying to shut it off really early as well as late. The power amplifier is getting shut off with the key as well as an early stage, because sometimes an early stage has got enough power to actually sneak out the antenna. They call it back wave. And this will shut that off too, so you don't have any output at all coming out of it. And rather than run this model, I'm just going to show you what the output of it looks like. Here's the output. Now this is, obviously this time frame is not like you'd really have. Even at 20 words a minute, a DIT is going to be 60 milliseconds. So this one will only be 3 milliseconds. But this is showing you the keying, okay? It's not a sharp cutoff or rise which you don't want. You want that slope in there. That's why all this extra circuitry is here, to make it slope off with the capacitors charging everything. But this, you can see the whole waveform now, and you can actually model, you can say, how much power am I getting out of it? Well, I'm getting 45 volts to minus 45, so it's 45 peak. 45 times 0.707 is what, 30 RMS. You square that, you divide by 50, and there's your power. And so this is putting out about 20 watts of power right now. That's my next transmitter that I'm going to have. It'll grab an amplifier. But this is what I'm building now. And basically, I mean, you can lay it all out here. I can see what it's going to look like. You can see what the components are. See how it's going to run before I even put the first solder there to a pad. So, that's what I wanted to show you. This was the reference sheet that I had all, a whole bunch of them printed out, ready to go. But basically, this shows you where you can, I'll email it. Shows you where you can load it, LTspice download with this. It's too long to, get it from your analog devices. And then there's a couple of LTspice tutorials if you want to play with it. They're really nice. This first one is done by Nick Kennedy. Bert and I know him very well. He goes to OSAPCon every day, every year. And he did a really nice tutorial. It's available out there in PDF form. You can take a look at it, run the simulations yourself. Very nice. Nick is an interesting character, really an experimenter. He just retired also. He used to run the largest nuclear power plant in Arkansas. So he's experienced for all kinds of things and very interesting to talk to. But very nice LTspice. We talked to him a lot. And then there's another one that I found online which also seems very nice. I don't know who did this one, but it's there and it's free. And once again, it steps you through probably in a little different detail than Nick's does. And if you want to just play with it, play with some circuits, let somebody show you step by step, because I know a lot of this is going to be gone, you know, until you get in and play with it a bunch. But some of these tutorials will kind of step you through it too.
So you're going to put those on the website?
Yes, I'll put this sheet out there so you can pick this up, and yeah. So
It's free, right?
it's all free. Yep. And LTspice is all free, which is wonderful. That's the beauty of it. It really is. Okay, John.
Yeah, really nicely done. One thing that's cropping up lately is FM phase noise and oscillators.
Yeah.
What will that do a noise analysis on basic oscillators that look at the phase noise, not the AM noise?
I'm not sure it's going to get that amount of detail. It depends on the model you have for the oscillator, and I'm not sure you're going to get it accurate enough to actually see that kind of thing in there. I wish it could. You almost have to use a spectrum analyzer and hook it up to see the real thing rather than a simulation, unfortunately. I've never seen a way of being able to measure phase noise. That would be nice. I'd love to do that, but really we're doing much more basic pieces than that.
Yeah, I understand here, kind of hobby level.
Oh yeah, but that would be really nice. Phase noise is a big deal. So, anybody else? Any questions? Yes.
Free version of LTspice has got kind of limited capabilities, and I forget what the staff is on limit, like how many.
Well, I don't think.
transistors.
You think it is? I don't think it is. I think it's wide open. As far as I know, it's, unless they change it since analog bought it, but it was been wide open as far as I've known.
Oh, okay, so you can.
Maybe too much. That's typically printed circuit board, things like that. Express PCB and some of those have a limited, or Eagle, or some of the student versions have a limit as to how many components or the size of the board or whatever. This is wide open. They want you to use it. You know, they want to give it to you so you buy their LTspice parts. And I think they're getting more analog parts now in the models too. They're adding them as they go. But once again, I'm going to use a power amplifier, 16-watt power amplifier coming out of it, RD16 HHF1. I don't want to use push-pull coming out of my new transmitter. I was able to find a model for that thing, and the model's perfect. In fact, that one, my more advanced transmitter there, had that one on the final amplifier. I didn't show that. That's how I got the 45, which was about 22 watts coming out of it, 20 watts. And with a more powerful power MOSFET amplifier in there. Yes?
It was the Texas Instrument one that limited your 3D.
Oh, okay.
Now there isn't even a 3D. I think that's the only, LTspice is the only 3D around.
What do they call it? TI? No.
TINA.
TNAT, yes.
That was a very nice simulator.
It was. I've used that too.
Yeah, but now you gotta buy it. It's really verbose and well out of proportion for personal use.
So, yeah, if you do it for a company and you have some particular parts they have and they have the model for it and it's the only place you can get it, well, sometimes you have to do that. It's been so interesting to watch. This also used to be when the government first developed it, a line by line thing. You have to type in the node names, you know, that I have a node from this point to this point, it's the 500 ohms, and you put it in a line, and the next line, I have a node from this one to this one. You have to draw it out on paper and then enter each one of these lines, each one of these components. It was hideous. And then the output would come out, once again, on a graphical thing. You could print it out on a roll of paper, and you could see the waveform coming out on your printer. And you know, it worked. It was fun to play with, but it was not, the user interface is what makes the differences between the various spices, whether they're worth it to you or not. So, yes, Mary?
Yeah, there's also another
Yes.
simulator
You've
made
got it.
by, it's called Multisim.
Multi-sim, Merch is
It's
it?
made by, I can't think of the company name, but it's in North Dakota somewhere. And originally it was called Electronic Workbench.
Yes, yes.
It originated in Canada, and then the company in North
Yes.
Dakota picked it up. And they call it Multisim. It's very good.
That's got some,
But it's all based on the spice, you know.
yep, but it's got some user interface things that are really nice in there. Like they have a little ammeter you can hook up to it.
Yeah,
You
you
hook
have
between these
sort
two.
of meters that you can.
You can put the
connect.
meters at a different spot on your mall, and it'll show them up, you know, when they.
Yeah. It's
when they
just
move.
like you're working in your lab with all these.
I used that for a long time too, but I ended up switching over to LTspice because of the models that are available and the ease of use. The easy way of adding to the library and the way it's supported so well. That's why I ended up switching over to LTspice, and as I say, it's become kind of an industry standard now in some respect. Lots of, as I say, the colleges are, I don't know if you use it in your, say, town. You use multi-sim, okay, that's fine. And a lot of them do that, but it's just, whatever they get onto it, and once you get either a corporate license or a school license, and you can, you know, because that usually costs something, I think multi-sim does. Maybe not the beginning one, but I think when you add on to it, it does. So, once again, it's a good simulator, and it's got lots of pieces that LTspice doesn't, possibly, so. Any other questions? Well, you know, sometimes we want to set up a, thanks. We want to set up a time that we know we could try out some things here. PC, if you have some questions on it, you know, we could actually do that before or after meetings or something. We could actually try out some things that you have that, you know, we can play with it, so. Anyway, okay, well, hope you enjoyed it.